So, yeah. Hello, everybody. So, yeah, my name is Léo Théodore. I'm from the École des Mines de Saint-Étienne in France. So it's my third year as a PhD student, and today we'll talk about deep learning-based instance segmentation to characterize the morphology of compact aggregates through image analysis. So our dream job, I guess. So as I said, what I'm going to talk about today is a part of my PhD thesis. We are trying to understand how some latex nanoparticle aggregates form under hydrodynamic constraint, right? And here you can see some images, some pictures of those latex aggregates. And what I'm really trying to do is to characterize the morphology of those aggregates, right? And not only the 2D morphology, but also the 3D morphology. So we're going to talk a little bit about that later on. And why is it so important? Maybe you may ask, right? Why is it so important to characterize the morphology of such aggregates? Well, I believe that you all have a smartphone, for instance. Maybe you have a laptop, I don't know. Well, you may know that almost every plastic part of those devices are made of latex nanoparticle aggregates. When we dry those aggregates, we get a powder, and this powder is used in a lot of industrial process. So it can be, again, as I said, the plastic part of your laptop, of your smartphone. It can be the plastic part of a car. It can be, maybe if you took the plane to come here in London, you wrap your bags with a lot of plastic. So here again, we can find those aggregates. And actually, depending on what we want to create, we are seeking different morphologies. So maybe we want to have a very narrow distribution of size. Maybe we want it wider. Maybe we want the aggregate to be very small, very large, very smooth, or maybe we want them to have a lot of texture. So that's why we're doing what we do. And basically, as I said, when we have pictures, we have only 2D pictures. And it's sad because actually, we can only measure 2D characteristics on 2D pictures. We can only measure the area, the perimeter, what we call the circularity. And what we really want to know are actually the 3D characteristics. So the volume, the surface area, which is actually the exchange surface. It's crucial in some application. We want to know the sphericity and so on. And well, we cannot directly do that. So what we're trying to do is to acquire some images. So we have a big tank. We fill it with an acid solution. We fill it with a latex nanoparticle. We heat that up. We shake that. And then we get those beautiful aggregates that you can see here, some in situ images. They are not always as beautiful as those ones, but usually we can still see something. And we can use a segmentation model to segment those images and get some segmentation masks. And on those masks, we can make some measurements, and we can have already some 2D measurements. So we can measure the area, the perimeter, and so on. But as I said, it's not enough. What we want to have is a 3D morphological characteristics. So what we're trying to do right now is to fuel this segmentation mass into a generative model. And so we can build a digital twin. And so we actually have a 3D representation of the real population of aggregates, right? With a generative model, so using the generative AI. And since we have a digital twin in 3D, what we can do is use those 3D representation to compute some 3D morphological characteristics. And now we can know what the volume distribution is, what the surface area distribution is, and so on. So that's the basic idea of what we're trying to do. Sadly, unfortunately, today I will only talk about what's in the paper that I presented. So we'll only talk about the segmentation part, but fear not, because there is a lot to talk about, right? So basically today, what we're going to talk about is this. So we have an experimental setup that allow us to capture some in situ images. So we have a sphere tank we have a LED, which is a lighting source, right? And we have a calibration grid, so we can know what we're measuring. And we are capturing some in situ images. And then we need a segmentation model to, to compute a lot, as many as possible, segmentation masks. And we want those masks to be as accurate as possible. So the measurements that we will do are very accurate. Again, the issue here is that when we think about segmentation models, usually they are trained on the COCO dataset or the ImageNet dataset and so on. They are not really trained on those kind of objects. So we need to retrain those models, right? So yeah, so the first thing that we are going to talk about is how to build a training dataset that is representative of the real data. Then we will talk about the two other parts, or we need to choose a segmentation model and we need to train the model. So actually we will compare several segmentation models, and we will, well, obviously we will see that we found the best model for our particular application, and we will apply this model to real images and see what we can get in terms of information. So first, building a training dataset. So as I said, when we think about segmentation models, there are a lot of models. There are, you know, the mask RCNN architecture. We can also use YOLO. We can use, there is SAM. I will talk about that a little bit later on, but there are a lot of models. But again, as I said, they are usually pre-trained on the ImageNet or COCO dataset and so on. So we needed to create a dataset that is representative of the real data. And in order to do that, we used the sphere model, which is a well, it's a stochastic model to generate aggregates or granular objects. Sphere as in stochastic process for highly effective radial expansion. Basically, what we do is that we generate a base shape, which is an ellipsoid. So we can control with two parameters, the size and the shape, the elevation of the ellipsoid. And then we are using some random fields. Here we are using Gaussian random fields to tweak the morphology of the base shape. So actually, with those random fields, at every point in space, we have a value, and this value will allow us to move every vertex of the mesh of the ellipsoid. And so with some random fields, we are controlling the overall shape, the general shape of the object. And with some other random fields, we are controlling the fine details of the mesh, or the shape, right? To give it some texture, some angularity. So basically, that's what we can, that's some examples of objects that we can create with our model. We are using 4 Gaussian random fields and for a total of 10 parameters. So it's highly flexible, and we can generate like 1,000 objects in less than 2 seconds. So it's really quite fast when we compare it to other models that are used, for instance, in the discrete element method field, where usually it's like 10 times slower usually. So it's really quite fast, and we need it to be quite fast because we don't want to spend days generating a data set. So a lot of information here. So what we did and what we saw is that on real images, as you can see on the left, both lefts, what you can see is that we have very different lighting conditions. Maybe you cannot really see, but there are also really different noise blur conditions. So what we did is that we created 2 different datasets that you can see on the right, dataset 1 and 2, that are also fairly different in terms of lighting condition and also density of objects and so on. And so we have more than 400,000 of aggregates in total that we use to compose a total of 2 times 2,000, so 4,000 images. And it's fairly basic. Again, we have the base shape. We deform the mesh, we add some lightning, some noise, some blur to get a more realistic aspect. Then we control the image, and then we can see that it kind of looks like the real images, but we wanted a real measure of this kind of look like the real image. So what we did is that we computed what we call the Fréchet inception distance. So maybe you're not all familiar with the FID. It's a distance that was fairly used when we first introduced the GAN architecture. So it tells you basically if an image looks like another one in terms of human vision. The issue that we have with the FID is that when you look at the literature, sometimes you can see that if you're below 100, it's fairly good, and sometimes if you're below 50, it's really excellent, and sometimes just like if you're below 200, it's good. So it really depends on the image that you're looking at or on the set of images that you're looking at. So here, and that's what you might be able or may be not able to see on the right. What we did is that for every data set, we were thinking that, okay, this data set one, we need to compare it to the data set A of real images. So what we did is that we took some subsets of the data set of real images and we computed the FID between those real images data set. And so what we saw is that actually the curved line. So the curved line, it decreases and it tends toward the value of so it's like 66-ish something for the first data set and 25-ish something for the second data set, which are fairly close to the values that we get when we compare this time real images to synthetic images. So it gave us a benchmark of what kind of FID we should be aiming at. So so anyway, that's how we built our training data set. And then we needed to choose the best segmentation model. So what we did is that we looked at the literature. First, we tried obviously some direct segmentation methods such as OTSU for the global thresholding. We tried some adaptive and local thresholding, but it took a fairly huge amount of time, and we wanted to tend toward a real-time application. So we didn't choose any direct methods. We also tried UNet, but the issue is that we can have very blurry objects and sometimes very crisp edges. So it was not really suitable for this application. And also we had a huge amount of overlap. So again, UNet was not the best choice. So that's why we used instance-based segmentation models. So we tried the math RCNN architecture. At the time, YOLO V8 was state-of-the-art. So now it's YOLO V10, sadly. Also, SAM was state-of-the-art at the time. SAM is a segmentation anything model from Meta. If you heard about it. So it's a multimodal model that we tried. We retrained these models from the COCO dataset. So it was previously trained on the COCO dataset, except Sam, she's trained on the Meta dataset. For YOLO, we trained the medium-sized model and the largest model because there are five different architectures: nano, small, medium, large, and X. So we tried medium and X. For some, we just took the largest model. And for ResNet, we used 50 and 101. We didn't try 152. There are some papers that showed us that maybe it was not, maybe the gain in terms of performance was not, I don't know what I was saying, but anyway, I was looking at the time and I was like, I need to hurry up. So anyway, we didn't try 152. So we trained all those models on our training data set. We computed all the common metrics that we usually compute. So we have the average precision, which is computed from the intersection over union. We have the mean intersection over union. So these two first columns really tells us if the segmentation masks are actually accurate. So we really need to look at those first two columns. The accuracy, it doesn't provide us with a lot of information actually. So we really discarded that because the accuracy was fairly high for every model. The precision was not the best metric here because again, we wanted the segmentation mask and not the background. So the recall F1 score were very important to us. And the average relative error, well, it just tells you if you have detected an object, how many masks do you have? So no, I won't say it like that. If you have an object on your images, have you detected like 0, 1, or maybe more objects? If you have detected one object, then the error will go down. And if you have detected 0 or more than one object, well, the error will go higher, right? So as we can see, actually, YOLO is fairly good on the last column. So it tells us that YOLO is very good at detecting objects. Sadly for YOLO, that's not really what matters to us. We are not aiming at detecting every single object. We are aiming at detecting enough objects to be statistically representative of the real data. But we really want the segmentation masks to be fairly accurate. So that's what we can see with the first two columns and the recall and F1 score. So obviously, as you can imagine, that's why we chose the mask RCNN ResNet 101 architecture. So here we cannot really see anything because actually for our particular application, what really mattered was not the common matrix that we just previously saw. It was more the distribution of morphological characteristics, right? And that's what we can see here. So we have the equivalent diameter, the security, the convexity, which is the ratio of area over convex area. And what we can see is that, yeah, for the size, pretty much every model is kind of good, maybe except some. And for the rest, it's, yeah, you cannot really see anything, but, or maybe actually you can. So, yeah, let me just jump to the conclusion. So the ResNet 101 architecture or mask RCNN was really the best fit and really gave us the best results. To compute a metric for the matching of the distribution, we use the total variation distance, which tells you if two distributions are fairly close or not at all to one another. So yeah, it works fairly well. So that's why we chose that architecture and not the, as you can see, YOLO sometimes gave us some pretty bad results because some pixels were slightly off. YOLO really likes to give us some convex segmentation masks, and sadly, well, the objects are not always convex. So sad for YOLO. Anyway, one last thing. So we applied those results. So we used our segmentation model, trained segmentation model to real images, and we get some results. And sadly, we can see, we really can't see any difference between the three data sets that we had. So we had three data sets that were images taken at 3 hours, 7 hours, and 10 hours of the aggregation process. And what we can see that we don't see any difference. The good thing is that, yeah, it was consistent with the, yeah, it was consistent with the observations. So anyway, what I just said, and so for the future, we use the segmentation mask to fuel our generative model and build the digital twin I talked about, and we actually get pretty good results currently. Yeah, thank you. Oh yeah, thank you very much. Thank you.